Welcome to section 14.2 Symmetry. Remember to take notes along with me, complete the examples in all the U-tries and explorations. This is what we will be covering. So symmetry is an area shared by mathematics and quite frankly all around us, the natural world and art. So it is really appealing and young children really like it also. And because repetition is something that helps us learn, maybe our enjoyment of repetition makes symmetrical designs appealing. So when we look at the natural objects in the world around us, we're going to find a mix of symmetry and asymmetry. Plants have symmetrical parts, even if they might not be symmetrical all over. Leaves and flowers are usually symmetrical. There's all sorts of spaces. So just as the concept of circle has an informal or artistic interpretation as well as a mathematical definition, the notion of symmetry has both an informal interpretation and a specific mathematical one. So children in elementary school first learn about symmetry informally by matching parts. And then we consider a more precise mathematical definition of symmetry, which requires that we use the transformations just studied, rotations, reflections, and translations, to define symmetry. In other words, we use these transformations to say what it means for a shape to have special kinds of symmetry. And then we can actually create symmetry. So there are four kinds of symmetry that a shape or design in a plane can have: reflection symmetry, translation symmetry, rotation symmetry, and glide reflection symmetry. And we're going to use our transformations of reflections, translations, and rotations to say what type of symmetry a shape or design has. So let's start with reflection or mirror symmetry and the line of symmetry. So if a shape in a plane has reflection symmetry, there is a line in the plane such that there are matching parts when the shape or design is folded along the line. So in other words, the shape or design as a whole occupies the same place in the plane both before and after reflecting across the line. So take a look here. Notice that reflecting across the line of symmetry causes most points on the design to swap locations with another point on the design. But the design as a whole occupies the same place in the plane. You can have more than one line of symmetry. So let's see here. Here's one line of symmetry. And you can see that this is the shape. And what it does is it kind of takes its points back onto itself. Now you can have more than one line of symmetry, which means if we look at it this way, this point goes to this point. But if we look at, say, in this direction, or actually let's go in this direction. What we're saying is that this point goes to this point, and this point goes to this point. So there are all different kinds of lines of symmetry. In fact, there are 4 lines of symmetry in this design. So to determine whether a design or shape drawn on a semi-transparent piece of paper has reflection symmetry with respect to a certain line of paper, you can just fold the paper along that line. And if you can see that the parts of the design on the 2 parts of the paper match, then the design has reflection symmetry and the line you folded along is the line of symmetry. Another way to see whether a design or shape has reflection symmetry is to use a mirror that has a straight edge and place the straight edge of the mirror along the line that you think may be the line of symmetry. So here if you have your paper, and let's say you've got this kind of shape here, if you were to fold and it would land back on each other, you would see that it had it would have symmetry. Instead, if you had this shape and you placed a mirror, that's your mirror. If you see back the exact image on the other side, you could say, hey, that has reflection symmetry, and that's the line of symmetry. And you can also move that mirror around in different spaces. If you had a mirror here, you could place a mirror here, you could place a mirror here, you could place a mirror there. And that's all the different lines of symmetry. So compare mathematical reflection and reflection symmetry and explain how these are related. So a mathematical reflection was covered in 14.1, and that's where we're shifting a point or a shape over a line of symmetry, right? We were taking those shapes over a line of symmetry. But reflection symmetry is when a design or a shape contains at least one line of symmetry. So here we're kind of moving things around, and here we're identifying already in the space. Let's talk about translation symmetry. So a design or a pattern has translation symmetry if there is a translation of the plane such that the design or pattern as a whole occupies the same place in the plane both before and after the translation. So true translation symmetry occurs only in designs or patterns that take up an infinite amount of space. But when we draw a picture or design that has translation symmetry, we only look at a portion of it. So we kind of have to imagine that the pattern continues forever. So in fact, notice that this pattern has two independent translations that take the pattern as a whole to itself. One is a shift right. So again, this guy here, this image here, shifts to the right, and then it becomes this image. Another is shift up. This here shifts up and becomes that one. Wallpaper patterns generally have translation symmetry in two independent directions. So you could think of it as left, right, and up, down. Left, right is kind of one direction, and then up, down is two directions. Frieze patterns, which I'm pronouncing 100% wrong. Frieze, I believe, is how they're supposed to say it, but quite frankly, I'm not sure, and I have looked it up, and I haven't gotten a clear answer. So frieze patterns, I'm sure my art students will message me and tell me how to fix it. Often seen on narrow strips of wallpaper positioned around the tops of the walls of a room, provide additional examples of designs. So this pattern here has translation symmetry, but it's only in one direction. This image here is just moving to the right and to the left. It's not moving up and down. And so it's only got one direction instead of two. So we want to compare translation and translation symmetry. So a translation is we're shifting a point or shape a set number of units. Remember those vectors, set number of units in a direction. However, translation symmetry is we're shifting a whole design in a direction and replacing it, and it's always being replaced. So if we kind of go back here, we were shifting it to the right, but then something was already replacing it. We were shifting it to the right and up, and something was already replacing it. So you can kind of think of it as like multiple images, whereas this case we're just taking one image. Rotation symmetry is if there is a rotation of the plane of more than 0 degrees but less than 360, such that the shape or design as a whole occupies the same points in the plane both before and after the rotation. So for example, we're going to rotate this 72 degrees about the center. So here's the center. So if I was to rotate this point 72 degrees, that's got to be 72, right? What's going to happen is this point also gets rotated and it replaces that one, and this one replaces that one, and this one replaces that one, and this one. And so it's always before and after the rotation. You can't even tell that it was rotated. Another way to kind of think about rotation symmetry is fold symmetry. So if we kind of go back to this one, if I were to fold this up, I would fold this 5 times. 1, 2, 3, 4, 5. I've got 5-fold rotation symmetry. Because by applying 72 degrees equals 360 divided by 5 rotations about the center of the design 5 times, all points return to their starting point. So generally shapes or designs have n-fold rotation symmetry. We can even identify, hey, they have symmetry, rotation symmetry, but we can go further. So in this case here, we can see that this point, if I rotate this, it's going to go over to this point, and this point is going to rotate back onto itself, but it folds twice. Here, this has around the center point, right? This is going to go to here, this is going to go to here, this is going to go to there. That's 3-fold symmetry. This is going to go to there, 1, 2, 3, 4, back to itself. This little guy, 1, 2, 3, 4, 5, 6, back to itself. So you can determine whether a design or shape drawn on a piece of paper has rotation symmetry if we make a copy of the design on a transparency and then place this transparency over the original design so that the two designs match one another. If you can rotate the transparency less than a full turn, remember it's got to be less than 360, so that the two designs match one another, then the design has rotation symmetry. So if you've got kind of your original design, and let's say you've got, it looks something like that, and then you've got your transparency over it, and you draw and you take this shape and you turn it, and if you land on itself before the end, right, then you can kind of see how many times you've done that. So rotations, we're rotating a point or a shape about a center point. But in rotation symmetry, we're rotating within the design. We're not creating any new points. Here we're kind of end up with new points, new shapes, but here it's kind of within itself. And when we come back, we will continue to explore and do some more examples of actually finding symmetry.